When I was approached to do a guest lecture, I was immediately thinking about AI, because that's kind of what we do. And even though I'm not that much in the process control field anymore, I found it very interesting to go through and get a feeling for what the applications are these days, for AI in process control. So this is a very busy slide. So I've made some builds, but just so that we're all on the same page when it comes to talking about modern AI. AI is an interesting idea because as long as we've had the ability to automate computation, we've imagined that machines will one day be able to think in inverted commas. I have an internal definition of AI, which is really just that AI is everything where machines are doing computation instead of brains. In the same way that mechanization is machines doing things that we could do with our muscles, or obviously even more things. According to my definition of AI, a hand calculator is a piece of AI, which is not what the current idea is. If you're talking to a modern person about AI, and I've had courses in AI, which didn't really focus as much on deep neural networks as we are focused now. But this slide for me summarizes what I think of as being modern AI. In other words, starting in 1950 with mechanical tube and relay-based synapses. Marvin Minsky built this thing in 1950. And it could actually do things. It could solve mazes. They used a primitive kind of backprop and update machine to get it to learn things. There were mechanical perceptrons. There were all kinds of things there in the early 50s and 60s. And then the same person, Minsky, published this paper, Perceptrons, which kind of showed that single layer perceptrons couldn't do certain things, and the research on neural networks died. And so this was like the first AI winter, or one of the AI winters. And it only really came back into vogue in the late 80s, early 90s, when Jan LeCun applied convolutional neural networks to handwriting recognition. And part of the problem was that it was always very computationally intensive to train neural networks. I remember in the 90s, I still learned from a red book written by Bishop about neural networks. And, it's a universal approximator. So you can, with one hidden layer, you can always approximate in any arbitrary function. But you have real problems with the number of weights. As the number of weights explodes, it becomes really difficult to train. And that whole piece from 1950 to the late 2000s, people were very down on neural networks. I came out of my artificial intelligence class, which at the time, artificial intelligence was not in vogue. And so the class was just called pattern recognition. And during that entire time, I came away thinking neural networks are, not good for much. And the big AI thing that happened when I was at university was that Deep Blue beat Kasparov. And it's maybe interesting for a modern person to think that these early advances, this kind of landmark of a computer beating a person, was completely rule-based. There were no neural nets. It was old school search and pre-built rules. And if you fast forward to 2016, this is now when they started using deeply layered neural networks. Now, I'm assuming that most of the people in the audience will at least know roughly what a network topology is. But we went in the 50s from kind of one hidden layer to where we are now with hundreds of layers with, billions of parameters. But in 2016, in other words, just about 10 years later, 9 years later from Deep Blue beating Kasparov, AlphaGo beat Lee Sedol in a different game, Go. And that particular game engine had no symbolic AI. So in other words, Deep Blue, no neural nets, now all neural nets. And you'll notice I had to use like a logarithmic scale on this timeline because to fit everything in that has happened in the last couple of years in terms of the application of deep neural networks is just crazy. You've got AlexNet, which was image recognition. You've got Word2Vec. You've got general adversarial networks. You've got GPT-1, 2, 3, now 4. You've got DALL-E, ChatGPT. All these things happened within after 2010. So we are seeing really a rapid expansion of not only the abilities, but also the applications of these machines. Now, I think a really interesting layer to add over this is to think about what happened to our field, the control field, in the same time. Now, I've only put in these 2 dates because really, I think modern MPC are like elaborations in many cases on DMC. You can say that there have been a couple of interesting control advances, but it's mostly of a practical nature. I tend to think Lyapunov probably solved almost all of the stuff that we want to think about. And that all happened in times before I was born. So I used to make quite a bit of money by going to places and applying techniques that existed before I was born a couple of years back when I was still consulting in the industry. But it's interesting to ask what is the effect on modern control these days. Now, another layer is the development of tooling. And I'm going to try and weave a couple of threads in this talk. Firstly, the base fact of the advances in neural networks, but combined with the driving forces and the tools that enable that to happen. Because that, for me, is the main way in which the control field is benefiting from the modern AI boom. Sure, there are some applications, and I think there will be applications towards the end. I'll talk about some things that we can do based on directly the AI that exists now. But I think one of our big benefits has been that as the industry has developed tools, we have benefited by from those tools. So I think if you were around in the 90s learning control, it was impossible to escape MATLAB and Simulink. I think to a certain extent that's still true in industry. And it's interesting to see that Python itself, which is kind of the lingua franca of modern AI, was actually released after Simulink. And you think of Simulink being, a graphical kind of product, maybe a modern kind of product. Another layer on top of it is the hardware support. Now, we went from these hardware tubes, we went through to general purpose CPUs, and that's been everything up until the late 2000s. That was all running on CPU. And then we saw the GPU revolution. In 2006, NVIDIA released CUDA, which was a framework that would allow you to interact with general purpose GPUs, graphical processing units. And those GPUs went from just drawing triangles on the screen to doing more general linear algebra to being able to do all these calculations that we are doing for neural networks now. And more recently, there were these 3 very high-profile libraries, TensorFlow, PyTorch, and JAX, that bridged the gap from high-level languages like Python, which weren't compiled down to GPU, to allow us to use those hardware in a way that didn't require us to learn some compiled language. So there's a couple of interesting things that happened. I think something that is useful to shed a light on how these things have been advanced is to look at one of the kind of poster children of AI at the moment. So self-driving cars and autonomous robotics. These are incredibly well-funded projects. And I think that they are one of the driving forces behind moving some of our optimization and control problems forward. because they are solving these challenges with budget that we don't necessarily see in the process control industry. And many of the techniques that they are using will be familiar to control practitioners. So at the front end, there's convolutional neural networks, and then LiDAR with sensor fusion for trying to understand how these scenes are put together. There are techniques called localization and mapping, or SLAM, for probabilistic filtering, and they use the techniques that you think of, extended Kalman filters, particle filters, combined with maps, and effectively it's a state estimation problem. The challenge is to understand, based on all these sensor data, not only where you are, but how fast you are moving, relative to all of these things, how fast they are moving, and so on, so that you can then solve these planning and decision-making problems. So that means that you are trying to predict the movement of things around you, your own motion, and you're trying to figure out how to get to a particular place. So that's routing, mapping, obstacle avoidance, and all that kind of stuff. At the lower level down, there's actual control execution. That's mainly MPC, PID, all the kinds of stuff that we are used to using. And then you have training sets that are trying to teach the networks that are doing the high-level orchestration of all of this with reinforcement learning. And kind of there are some trials in the direction of having perception to control networks, which are effectively, if you think about the idea of connecting MPC directly to valves instead of writing down to PIDs, that's the same idea, that you just have one big network that's doing all of the problem solving. So you can see that these people are solving challenges that we as an industry have been grappling with for as long as we've been in industry. Now, I'm going to take a little bit of a sidestep from this, because that gives you the kind of framework where you can see, oh yes, well, here's an application in the real world that isn't just on a plant that a normal person would have perhaps encountered or seen on TV, something like this. And maybe another thing just to also mention that, as AI is such a loaded term, I keep talking to people when I say, I do AI research, or I have done AI research, that mention things like these Boston Dynamics robots. Now, this happens to be the Atlas robot, and they've had very many YouTube videos dedicated to them. But one of the most interesting things about the Boston Dynamics videos is that there's almost no learning involved in those videos. If you look at it from the correct angle, it's really a showcase of the mechanical prowess and control of their platform. These machines are mainly using MPC and the kind of control techniques that I mentioned on the previous page. There is some very light AI and vision processing happening on board, mainly for things like local obstacle avoidance and recovery. But in general, when you see a video of one of these things throwing a bag of cement up 2 flights of stairs or something like that, what they are trying to show you is that this machine can do that and not fall over, not that they have, solved general AI problems. Although I think when you put something in a humanoid shape, people immediately confirm more intelligence to it than it actually has. Right, so I'm breaking this talk down into 3 different parts. We have the influence of all of this stuff on optimization, and I think optimization is the one big thing that we have in common. As soon as you start doing control, you start thinking about optimization. The second thing is the time series aspect of analyzing time series, where I think neural networks have had a big boom. And then I have to, of course, talk about large language models. So that's coming at the end for those of you who are only here to hear about ChatGPT. Don't worry, I'm going to be talking about that too. So an interesting thing about these deep neural networks is that you have these billions of parameters that you have to optimize. And if you think about a model like the GPT range of models, or Claude, or some of the open models like Llama, And you have all these billions of parameters. I'm not going to go into the detail of exactly how that training happens, but conceptually, you can imagine that it's optimizing some objective function by tweaking all of these different parameters. And what has happened, and one of the drivers of success in deep neural networks, is the development of stochastic gradient descent algorithms. So these are algorithms that are effectively modifications of like good old Newton, except that they are saving time by not evaluating a full gradient in all the dimensions of all those billions of parameters. They are choosing some stochastic number of directions in which to evaluate, and that they only optimizing in those directions. Now, there are as many of these algorithms as there are groups applying them. But you can imagine that that's a big driver. How quickly you converge, how your training works is a big driver. And it costs real money. These models run for months on incredibly expensive hardware. I think everybody knows that these big language models are out of reach for normal companies to do. You have to be one of these big companies with deep pockets in order to afford the compute of training one of these models. And these big companies, and quite notably Google, who's responsible for TensorFlow and JAX, in the process of developing these models, they have also invested in developing tooling. So for the linear algebra and auto differentiation and the effective assembly of these neural networks, TensorFlow, PyTorch, and JAX are kind of like the three big names in the industry. And as control practitioners, we get the side benefit of being able to use those units. So it's interesting that we haven't really seen a big lean into some incredibly low-level language, or a language that compiles all the way down to these GPUs in one go. You know, I mentioned Julia when I did my timeline, and while there are some very gung-ho people trying to get Julia to be the lingua franca, the reality is it's Python, and Python doesn't have the ability to run things on GPU by itself. The interpreter would be too slow anyway, but it has enough flexibility so that these frameworks can be built on top of it. So for those of you who aren't familiar, the basic idea is that you have a high-level language that you describe calculations in to varying extents of ease of use. I personally quite like JAX. And then these frameworks compile those codes down into a very efficient kernel that can be run on a GPU. And really, you cannot overstate the importance of the GPU, TPU / non-CPU architectures in these trainings. It would almost not be possible. The factors are factors of thousands or more between training on a CPU and running it on a GPU. So it's one of those things that the GPU manufacturers, like the shovel salesman for gold rushes, are going to be the big recipients of much of the wealth of these developments. But you have to kind of put into your head that you're not solving an optimization problem with 100 or 1,000 parameters or 100,000 parameters, but billions of parameters. And how do you actually do that? And these companies have had to solve those, and luckily they are in the habit of releasing those techniques back into the wild. So there's another piece of adjacent kind of tooling improvement that has caught my eye, which goes back to the thread of the symbolic AI. So I've recently been seeing a lot of talk about a larger kind of problem of constraint satisfaction problems. My pet version of this is Z3, which is written by Microsoft. It's a SMT solver, which is a slightly bigger problem than SAT. And SAT is just logical satisfaction. So, you know, if I have A plus B, if A and B is equal to C and A or B is equal to D, are there values for these variables that satisfy those constraints? it's a surprisingly ubiquitous kind of problem, and you can find those kinds of problems in a lot of different places. For those of you who are Python programmers, you may be interested to hear that the recent release of the UV package manager, that package manager solves the version allocation problem when you install Python packages by using a variant of these SAT techniques. And there's a massive difference between the kinds of things that you can do through brute force going through these constraints and what you can do with clever algorithms. Now, there's another link here with the rise of proof assistance. So ironically, although many of our advances have been obtained by neglecting these quote unquote symbolic AI methods, there is a new resurgence in symbolic AI. So posing problems as satisfaction problems, or using proof assistance like Lean and Rock to accelerate the design and verification of systems. And what's really useful about this is that all of these algorithms are packaged for wide dissemination. So you can actually benefit from these advances, and it's not some research effort that you read about but you never see. The last thing I want to say about optimization in the current epoch, the AI deep neural network epoch, is that optimization as a general field has advanced more than you might imagine. I will share the source if anybody wants it, but I came across this piece of research that shows that MILP performance has increased by 13 orders of, that's not 13 times, that's 13 zeros added onto the efficiency of MILP performance. Now just think about it. That means that you are able to solve problems that were completely intractable even just 10 years ago. But if you learned like I did these techniques in the late 90s, you really have to look again. A concrete example is that one of the kind of classic examples of an intractable problem is the traveling salesman problem. And that's usually in the context of being able to just approximate solutions. People will say, well, you know, this is NP hard, you can't really solve it. But in 2025, the Concord solver solved a problem of walking between all the bars in South Korea, which I'm still surprised that those researchers didn't just open 2 extra bars to get a nice round 82,000, but 81,998 bars in South Korea. And they solved that to optimality. It took them a couple of days, but it's still a feasible problem, which is really mind-blowing when you start thinking about transportation networks. These are techniques that are available to us, and most of us will never have, you know, real world problems where I need to try and route between 81,000 things. Maybe I just need to do local routing between 10,000 things, or, you know, a couple of hundred pickups in a delivery route. Now, coming back into control, the GPU acceleration that I mentioned before has now also reached stuff for like MPC, and the Akados library is able to do nonlinear MPC effectively in real time for quite large systems. And even for linear MPC, the QP solvers are getting really, really fast. I'm calling out highs here specifically because that's actually included in SciPy these days. So if you are using Python, you now have an LP solver, an MILP solver, and a QP solver built into your tooling without any additional install. So it might be time to rethink what's possible right now. If there were problems that you tried before, but they were running too slow, or you didn't know how to formulate them, they are now really imminently deployable. So here's a bit of visual aids about, so look at those, that's all the bars in South Korea. The salesman problem that they solved. And here's an example of a real world application of MILP. Now, I was struck by this because I've done some scheduling in the past, and these guys were doing lot sizing and scheduling in a batch plant. But what is really interesting here is that this is a 1 month period where they were fully optimizing the schedule. When I last looked at this kind of work, we were talking more about days and weeks. Now we're on months. So yeah, it's time to think about how big of a problem you can solve all at once. Right, so moving on to time series, it's one of the big things that have gotten a lot of, I think, media attention. Maybe I'm in very interesting media circles, but I see a lot of mentions of these forecasting and anomaly detection techniques. Now, I used to use dynamic time warping, which is a technique that was kind of perfected by Eamon Keogh. I'm mentioning that name because it's the same group that developed the matrix profile. Now that's a really cool non-AI motif and anomaly discovery algorithm that just kind of came up in the same time since I last looked at the field. But the content you are here to see is all the stuff that uses modern techniques. Now, I think the one that really gained a lot of traction in my world was this method or this library called Prophet, which was released by Facebook, then Facebook, now Meta. And they really changed the game in terms of how you were able to get good forward-looking forecasting for time series of a variety of types with a variety of seasonalities built in. And of course, a little bit later, the same people developed Neural Prophet. Now this is using PyTorch. It's many of the same researchers, and now they are adding a neural network layer onto Prophet as well. And now there are probabilistic and deep learning forecasting frameworks, Gluon, Merline, and there are a couple of time series foundation models are emerging as well. Now, why these are interesting, if you look at the graphic on the right, there are in broad strokes 3 different ways of thinking about this anomaly detection problem. You have the classic kind of idea that you have a good area and a bad area. And so these are good dots, and the things that lie outside of the good dots are these are good points, and those are anomalous points. But the network version of this is these days we are used to seeing this kind of encoder-decoder connection. So you have a system that takes some time series and encodes it in a smaller latent space, and you have a decoder that attempts to decode that, and you can then think of the difference between those two as being how interesting that time series is. So points that are far away from the reconstruction are possibly anomalous. Another way of thinking about the same thing is that you have your time series and you have a predictive model, and anything that happens in the real life that is far away from that prediction is anomalous. Now, there are a couple of different ways that have now been developed of thinking about anomaly detection that doesn't just boil down to this. But in my experience, the one take home from these time series for forecasting and anomaly detection is that they are overwhelmingly dominated by methods that are primarily autoregressive. Now, what that means is it's mainly involved in looking at the past input signals to predict the future output signal, but not in the way that a control engineer would recognize, because they, by and large, have this disdain, or they don't use exogenous inputs that much. In other words, they don't use things that are completely under outside control that you would need to do for process control, for instance. So I've had a couple of chats with people who have had this idea of, yes, I'm going to revolutionize control by using some of these time series libraries. Unfortunately, that's, in my experience, not where the big application lies, because while they are good for this kind of anomaly detection, they build in information that isn't completely causal about the causal in the input-output way that you want to have a manipulated variable cause and output. They tend to focus a lot on things where you have every input available to you, and you don't really have the ability to solve a control problem. So I would like to recommend this really nice paper, Foundation Models for Time Series Analysis. They have a really nice system of distinguishing between all the different foundation models and so on. I'm sure I'll be able to share the references for this talk afterwards. Now, in my particular interest is using these systems for system identification. And there the challenge is a little bit bigger, because the traditional control techniques that we want to use, in order for us to use those control techniques, we need tractable forms that lend themselves to the kind of optimization, at least closed form optimization, that we would like to do in order to solve the control problem. To include neural networks into models that are to be used for control is quite a challenge, but there are steps in that direction. So we have Neural ARX. I'm very excited by this advancement of what they call physics-informed neural networks. And in that system, what they do is they effectively include PDEs and ODEs into the loss function with the neural network, so that you then train the network to be physically realistic instead of just having good interpolation. So that allows you to train much better and use less data for physical systems that have this kind of stuff, some basis in reality instead of just random points. Another thing that's quite interesting is this chemical reaction neural network that recovers reaction kinetics from concentration data. So in this case, you are trying not to get to a kinetic model that looks like a simple kinetic model, but it does enforce mass action or Arrhenius laws during the training. So this is like effectively another one of those physically informed networks, but it's specifically for chemical reactions. And the nice thing about that is that you can get to a reaction mechanism that you can use in simulation without necessarily having to have a full set of reaction kinetics equations. It's also a little bit more interpretable than just having a random network. The question with those deep networks is always, how does it work? And it's quite hard to understand. There are also applications of hybrid models. Now, this is where you fit traditional, linear time series models, but you use the neural models to predict the residuals and augment in those to the prediction part of control loops. So that means you are still able to solve the control problem with easy equations, but then you're able to add in additional predictions about how those things will be different by using this neural residual model. So I think those are the main applications that I've seen in the system ID space of these kind of modern systems. Now we have reached the last piece of the puzzle, the thing that everybody is playing with these days. And definitely, if you're like me, you've been just overwhelmed with applications of these large language models. So while this last 20-year space is the time of the deep neural network, the last 5 or 6 year space is the time of the large language model. These models are neural network models, but they are specially trained on tokens, which are specifically representing human language. And at certain sizes of models, some emergent behavior emerges that allows them to suddenly be able to do things like answer questions or even reason in some cases. And I'm going to talk about the applications in roughly chronological order. And I think also in the order in which they are easily trusted. So I think that at this point, the main large language models are incredibly capable to do reading and summarization and question answering. I think summarization is one of the things that these systems do incredibly well. So if you have large repositories of operating procedures, safety manuals, that kind of stuff, and some of the models are multimodal. So you can feed it a PNID and it can read the diagram and tell you how things are connected to each other. This is an incredible time saver in getting a first overview when you are overwhelmed by new documentation. So you are being onboarded into a new plant, or you are trying to get your hands around a big system and you're trying to figure out what goes where. We all know that engineering is filled with documents, and you're trying to understand what should I do under these conditions, what should I do under these conditions. You don't have time to do operator training. You can summarize that with these systems. Now, there is a problem that while context token length is always growing, it is still too small for incredibly big sets of operating procedures. So you can't just feed in a full document into this LLM and have it just read it and understand it. And because of that, there's this technique called retrieval augmented generation. Now, what that really means is that the big documents are broken up into chunks. They are characterized by some vector that can be used to search later. And when you put in a query, that vector database is searched. The chunks of documents that are near the query that you are trying to, the query that you have posed, are retrieved. And those retrieved pieces of the document, or in some cases the whole document, if the whole document is small enough, are added into your prompt and appended on before the prompt is sent to the LLM. And that means that the LLM has more local context for the questions that you're trying to answer. Now, these techniques are really good, and there have been some early pilots where one of the topics that is very near to my heart is HAZOP. And anybody who's gone through a HAZOP process knows that you have to think about all these. Well, you have to go through the listed prompts. What happens if there are what happens in the reverse flow situation? What if there's no flow? What if there's gas instead of liquid? What if there's flammable gas, etc.? And these large language models can go through those transcripts, summarize, find gaps, figure out what questions haven't been asked, and so on. So they are incredibly useful for that. And I think there's going to be a silent change in industry where this is just going to be, it's going to be something that is irresponsible to do, is to do a HAZOP where one of these systems is not being used to follow up on the process. On the other end, these are generative models. And what that means is that they create new content. And I don't know that I've come across an engineer, definitely in my current job as somebody who works with computer or software engineers. I think that engineers are often quite allergic to writing documentation and manuals. And these LLMs are really adept at looking at code and writing documentation, and they can obviously generate code, they can write control scripts, they can do documentation, they can figure out many of the interesting syntaxes. So if you are using LaTeX, or if you are using, these days it's even in Word, you can just have a prompt, copy paste, and you are basically done. There is this issue of what they call hallucination. And, I put hallucination in quotes there because I think it's a loaded topic. The more we know about the way that human memory works, it's not that different, I think. One of my favorite quotes is that being wrong feels exactly like being right. We don't really have senses, although most of us think that we do, that would allow us to know when we are wrong. We do have this extra thing that these machines are very bad at, which is that we have a pretty good sense of when we are not sure. So if I am uncertain about something, I'm able to express that. But if you have interacted with one of these models, you will know that they are very bad at expressing uncertainty, because that idea doesn't really exist in the architecture that they are following. So at best, you can see whether you are in a low probability space in the training data. but that usually involves looking at parts that are not exposed by the commercial offerings. So the best you can do is, hope that the very confident answer that you have gotten is actually true. So this is why technique like RAG is much more important even than in the summarization case. Now, the last thing I'm going to talk about is this, the current trend to go to agents. Now, LLM-based agents, you can think of that as being similar to a control loop where you do a prompt, it does a plan, it executes, it observes, and then it reads back. And effectively, what the implementation of that is in code is that you are calling the agent or the LLM, and you are just prompting it to say, listen, if you want to call a tool or something like that, just tell me as the last part of your tokens, and the system then just interprets that last part as perhaps being a tool call. I've been having a lot of fun with Claude Code, which at the moment I think is the state of the art in terms of writing code, that are just able to independently solve problems in ways that we really haven't seen before. This is just running an LLM in a loop. It's giving it the ability to run system commands, change code, see the effect, write a piece of code that will check if that piece of code is working. And it's incredibly satisfying to get it going and then have a cup of coffee or stoke the fire and come back, and then it's actually produced something that is working. More recently, the most recent advance that's really being pulled together very well by industry is this idea of the model context protocol. And so this allows these agents to discover tools. Instead of having to build a tool framework yourself, you can hook it up to an MCP that knows the weather or allows you to interact with pieces of your plant or whatever. I've seen this recent example of agents for PLC that did PLC code-based code based on specifications. It actually is an agentic system. You can look at the paper. It's quite interesting. It's early days still. They were able to show that it was able to produce PLC mimics and interact with the PLC, right? Working PLC code. But I think this is the future that we're going towards is agents and increased kind of tool support for agents. So that brings me to the end. I'm looking at the time. I think I'm going to land it exactly on time. Let's just recap. I think that the modern AI trend has influenced process control in three big areas, right? We've seen this massive boom in improved solvers with autodiff frameworks and GPU support that are making nonlinear and combinatorial control possible at huge scale. So if you are in that field, if you're trying to solve a nonlinear MPC, or if you're trying to impose integer constraints, or if you're trying to solve scheduling problems, it's the time to, if you have given up on those problems before because of computational barriers, it's time to look again. In terms of time series, there are these amazing packages that are can be used for anomaly detection. Just keep in mind that many of the anomaly detection systems are based on kinds of models that aren't particularly useful for control. So you have to think about whether you're doing system ID or whether you're doing anomaly detection with these techniques. And of course, LLM agents. Right now, summarizing, writing, generating code, doing that kind of stuff. In the future, I see no reason why these systems won't be acting on plants or tuning controllers, running investigations autonomously, working together. I think maybe my call to action is that I think that there may be a use case for some industrial standardization. You know, OPC really changed the world of control interop, so that systems could communicate without having to implement low-level protocols themselves. And I think we need to get ahead of this boom as an industry and make sure that we are ready when the agents want to use our systems, that they are able to do that.